All right. So today we're moving away from radical functions and going into a different type of function called rational functions. Now, when you think of the word rational, what mathematical thing comes to mind?
Rational numbers.
Rational numbers, okay. But what makes a rational number a rational number? What? So it makes a rational number a rational number. Come on, guys, we had a whole lesson on this. So rational numbers. What typically is a rational number? Whole numbers. What else? Not just positive. They can be negative too. What else? So funky decimals we know are not rational, but can we still have decimals for rational numbers? Yes, but what has to happen to them? There's two things that can happen to them. What's one of them? They either have to do what? So 0.5, that's a rational number. That decimal ends. Or it has to repeat with a pattern like 0.33333 repeat. Now, the biggest thing about rational numbers is those decimals can then be turned into a what? A fraction. So that was what I was getting to. So with rational, keyword ratio, fraction. Rational means that you can turn it into a fraction. Irrational means you can't turn it into a fraction. So rational functions and equations, it's going to look like a fraction. So 1 over x or x over 2 or something like that. So that's typically what we're talking about with rational functions. So here's a very, very simple example of that. So there are 12 chocolates. 3 friends want to share them. How they divide the chocolates. So that's like a elementary school math problem. Obviously, if there's 3 friends, they want to share the chocolates evenly. How many do they each get? 4. You just divide 12 by 3, you get 4. Now, think about it this way. What if you tried dividing 12 chocolates among 0 people? How much does each person get? 0 people. So not even the person that bought the chocolates. Let's just say they're still sitting at the store. The store is 12. No one buys them. 0 people. How do you share it? Does that question even make sense? No, it's not possible. The question doesn't even make sense. Now, the reason it doesn't is because, does this make sense? Nope. What happens if you divide by 0? No. Nope. So in your calculator right now, do 12 divided by 0, see what you get.
Oh yeah, so you can't divide by 0.
You can't divide by 0. This is what we call undefined. All right. And if you think about it, why that also doesn't make sense, think about it this way. If we did the backwards, if we say 12 divided by 0 is some number, that means that we'd be able to do the backwards of it, which means we take that number, multiply it by 0, and it should give us 12. But we know that anything times 0 is what? 0. So it doesn't make sense. In math, this is what we call a contradiction. Because we know that any number times 0 is equal to 0. You can't get another number besides 0. So that's why we can't divide by 0. It just doesn't work. Shh. So, in your calculator, there are two things that it may tell you. It may tell you syntax, or it may tell you dividing by 0. Both pretty much mean the same thing. Now, I want you to think for a second. Syntax, where have you heard that before? It may not even be in math class. Where have you heard the word syntax before? I know you guys have heard syntax before. Have you heard it in English class? Yeah, you definitely have heard it in English class. In English class, what does syntax typically describe? So, in English class, syntax typically describes sentence structure, so how you word a sentence. Oh yeah, you guys have definitely learned this. So, syntax is just a fancy word for how you structure a sentence. Well, it's the same thing in mathematics. In mathematics, syntax is how you structure a expression in your calculator. So, for example, we've all done this before. Have you guys ever done like 4 plus, you actually put an extra plus and plus 3? Now, put that in your calculator exactly how I wrote it. 4 plus plus 3, and tell me what happens. Syntax. 4 plus plus 3. It'll give you a syntax error because can we have two pluses directly next to each other? No. We know that that's not the proper way to write a sentence. Okay? So that's typically what the error will give you. It just means that you just can't do it in math. Now, let's start by looking for some domains that we know about. So think back to the last unit, quadratics. The first example is a quadratic. What did I tell you is always the domain of a quadratic? Negative infinity to positive infinity. The domain of a quadratic function, any quadratic function, is always negative infinity to positive infinity, or all real numbers. Now, we talked about this one yesterday. Cubic functions. What I say is always the domain of a cubic function. I'm not cubic, cube root. So we talked about this yesterday. What's always the domain of a cube root? All real numbers again. Now, C and D, we actually got to do a little legwork. So if I didn't want to look at the graph for the square root of x plus 5, what did I tell you is the easiest way to find the domain? You do what? Shh. What do I do? Look at your notes from yesterday. That was like the last thing we talked about. What did we do? How do you get the domain without actually using the graph? Nope. So guys, under a radical, specifically a square root, what's the lowest possible number that we can have where the numbers will still remain real? 0, right? So don't we have to take what's under this radical and set it to be greater than or equal to 0 and then solve for x? Yes. Yeah. So if I subtract the 5 over, x has to be greater than or equal to negative 5. So The domain, you can say, is x is greater than or equal to -5. How do you say it in interval notation? So if x has to be greater than -5, that means -5 is at my highest or lowest number? Lowest. So it's going to come first, and it's equal to, so we use a bracket, and where will it go to? Infinity. So that's how you get the domain, guys. You take what's under the radical, set it equal to 0, or set it greater than or equal to 0, and solve for x. So we're going to do the same thing for d. So this will be 5x is greater than or equal to 4. X is greater than or equal to 4 over 5. So the domain, x is greater than or equal to 4/5, or from 4/5 to infinity. Either way, they mean the same thing. Now, errors on your calculator lead to what we call domain restrictions, because the domain represents the span of all real x values that are defined in the function. So keyword here, defined. Meaning it's not, if we put in our calculator, it's not going to give us undefined or an error. So let's look at this next one. So here's my question. This first one. This is actually a pretty generic rational function. Notice how the x is in the denominator. Think about this logically. This is a fraction. So 1 over some number, we're going to call it x. What is the only number that cannot be x? So in other words, what number, if I plugged in for x, would give me undefined? 0. So x cannot equal 0 because it would give us undefined. So our domain would be all real numbers except x cannot equal 0. So every other number will work except 0. 0 is the only number that won't work. Now, if this was on your test, I don't mind if you state it like this. You just got to make sure you say except x cannot equal 0. You got to tell me the one number that it can't equal. You could also state it in interval notation, which would be from -infinity to 0. Use a parenthesis because it's not defined at 0. Union symbol 0 to infinity. Again, I don't care which form you use. This form is definitely easier. Just know this is how you write it, like if you were doing it on your Delta Math or something. Now, this number right here is what we call the excluded value. So x equals 0, that's what we call the excluded value. It's the one value that does not work in this function. When we plug it in for x, it'll give us an undefined. So let's use that same logic for the next one. So we know that we cannot have 0 in the denominator, meaning that if I evaluate this, I cannot get 0. So to solve for what x cannot be, what do you think I should do? Nope. So what do we know that this denominator cannot equal? 0. So can I just set it equal to 0, solve for x? Because whatever x value will give me 0, that's the one that we have to exclude, because we can't have 0 in the denominator. So if I solve for x, I would add 4 to both sides, so 3x is equal to 4. X is equal to 4/3. That's the value that x cannot equal. So if we wanted to state our domain, it's all real numbers except x cannot equal 4/3. And again, if you wanted to do it in interval notation, it would be from negative infinity to 4/3 union 4/3 to infinity. Again, I don't care which way you state it. I think the first way is easier. But just know you may see it in the interval notation, so make sure you recognize it. All right. So letter C, what's the only part that I really need to pay attention to for excluded values? The what part? Starts with a D. Owen. The denominator. So I only care about this x plus 7. I don't care about the minus 9 on the outside. It's not going to affect anything. If that fraction becomes undefined, that's the issue. So I'm going to set it equal to 0 again. So x cannot equal what number? -7. So my domain is all real numbers except x cannot equal -7. So if I wrote an interval notation, it'd be from negative infinity to -7, -7 to infinity. And again, the reason that I separate it and use parentheses in the interval notation is because it's not defined at that number. So if you actually look at the graph and you make a table, the table will actually say undefined if you put in x equals -7. It won't have a physical point on it at all. So another way to ask the question, what value of x makes the function undefined? You will see it as, what is the excluded value or values, because you can have more than one sometimes depending on what's in the denominator of the domain. So if you see that question, it just means what value makes x undefined in the function. It just means set the denominator equal to 0, solve for x. And there's your excluded value. Or values. You can have more than one, but in this class, you'll mostly only have one. Now, why does this come into play? Well, that comes into play when we graph a rational function. So this is the rational parent function. So 1 over x is the typical parent function. So what I'm going to do is we're going to start with making a table in Desmos. So I'm going to go myself to Desmos. All right, and I'm going to type in 1 over x. So it's 1 divided by x. Now, the graph looks a little bit funky, but that's okay. All right. So if we think about this, all right, what value of x can definitely not be a value of x, or is undefined there? 0. So do you notice that when we have x equals 0, does it look like the graph is ever going to touch it? So it's that black line. Does it look like the graph ever touches it? Now, on Desmos, when you zoom in a lot, it looks like it does eventually. But if you zoom in close, does it ever touch? No. All right, there's a special name for that we'll talk about in just a second. But let's go ahead and get the table. So I'm going to generate the table. And I want nice, pretty numbers. Now notice when x is 0, what does it say it is? Undefined. So I'm just going to copy down this table because that's a nice, easy table. So we have -2 and -0.5. It's also, if you think about it, if you plug -2 in for x, it's also -1/2. If you want to think about it that way. -1, -1. 0 is undefined. 1, 1, to positive 0.5 or positive 1/2. So if I graph it, I have -2, -1/2, so it's about right here. -1, 1, 1, 1, 2, and 1/2. And if I drew the graph to look like the one in Desmos, it looks like this. Now, we know that x cannot equal 0. All right, we already know that. We know that x cannot equal 0. That's our excluded value. So if I was to write the domain, how would I write it? How are we writing them up top? So we know x cannot equal 0. So how would I write the domain? How would I state it? It's literally what we just did like 2 seconds ago. Good. All real numbers except x cannot equal 0. All right. And again, you can also state it as from -infinity to 0, union 0 to infinity. I'm just putting it both ways so you can see it. If you give me this on the test, I'm happy. Now, I want you guys to think about this logically, the range, so y values. So think about all the different values you can put in for x. So outputs. So remember, like if you plug in 2 in for x, you get 1/2. 3 in for x, you get 1/3. 4 in for x, you get 1/4. What's the only value that you can think of that you will never get, regardless of what x value you plug in? 0. Why? It is 0, but why? Why do you think it's 0? Can we divide by any number and get 0 ever? No. Because if we divide by 0, it's undefined. The only way you can divide by a number to get 0 is if 0 is in the numerator. So another excluded value, y cannot equal 0. So if x can't equal 0, y can't equal 0. Thus, what do you think the range is? All real numbers except what? Except not just 0. Y cannot equal 0. You got to put the x cannot equal, y cannot equal. You got to be specific. So -infinity to 0, union 0 to infinity. So y can also not equal to 0. Which, if we look back at our Desmos graph, let's say I put in y cannot equal 0 or y equals 0. It's this green line. Does it look like the graph will at any point cross that green line? Nope. If I zoom in a lot, there's still clear space between them. Now, why do you think I actually put these lines in? Well, there's actually a special name for these lines. They're called asymptotes. That's why I also graph them on this graph. And an asymptote is simply just a line, whether it's vertical or horizontal, that your graph cannot cross. And typically, there's 2 types of asymptotes. You got your vertical asymptote, which you'll typically write as x is equal to some number. Your horizontal asymptote, you'll typically write as y is equal to some number. In other words, if we wanted to write it down for this graph, our horizontal asymptote is y is equal to 0, because that's the line that it can't cross, where our vertical asymptote is x is equal to 0, because that's the line that vertically it can't cross, the x value that it can't, that's undefined. So this is your vertical asymptote, the purple line. This green line's your horizontal asymptote. And again, it's just the x and y values that typically is undefined in the function. And your graph physically will never cross that line. All right, so this is the parent function. This is generally what the function will look like. Now, with your normal graph, this is typically how you'll normally see the graph. So y equals a over x minus h plus k, where the translation of k over x is h units horizontally, k units vertically. The vertical asymptote is typically x is equal to h. So how you get it is you set x minus h equal to 0, solve for h, that'll give you x is equal to h. So another way you can think about it, you can flip the signs of h. The horizontal asymptote is whatever your k value is. So it's always y is equal to k. And you have to put x equals y equals. If you don't, and you just give me a number, I'm counting it wrong. I can tell you that right now. You gotta put the x equals y equals, depending on whichever asymptote you're talking about. Now, the a value, so this value right here, that tells us how far the graph has been stretched from the asymptotes. All right. So what do I mean by that? Let me actually show you a little demonstration here. So you don't need to do this, but watch this. So I'm actually going to type in the function that they gave me. So y equals a divided by x minus h plus k. And I'm going to create sliders for all of them. So a is 1, h is 1, k is 1. Actually, let's make k 0. So that is the, and this is 0. So that's the parent function. Now, if I move the a value, look at what happens. As it gets bigger, it gets farther away from the asymptotes. As it gets smaller, it gets closer to the asymptotes until it turns negative, and then it flips. All right. Now, let's say my h value. So watch this. So when I move my h value, still at the parent function, it shifts the graph vertically because the asymptote changes. So now the vertical asymptote is at 2. Now it's at 3.6. If you go in the other direction, same thing. It just shifts vertically. All right. Now let's look at the k value. So that's our horizontal asymptote. It moves it up and down. So that line that it can't cross moves up and down. So you guys see how the asymptotes affects the graph? Yes, no, maybe. Yeah. All right. It literally just moves it around. So if I go back to here, let's actually look at this. So whenever you graph, the very first thing that you should do is identify your asymptotes, which, by the way, if you can identify your asymptotes, you got your domain and range right there. All right. So let's start by identifying my asymptotes. So let's start with vertical. Remember, vertical asymptote, you would take the denominator, that's your x value that you have to exclude. You would take your denominator and do what? What have we been doing to get the excluded value for x? We take the denominator and do what? Set equal to 0 and solve for x. So x cannot equal what? 4. So your vertical asymptote is at x equals 4. So if I draw it, it's right here. And whenever you draw an asymptote, make sure you use a dotted line, because it's technically invisible if you look at the actual graph picture, but we use it to kind of guide us where our graph's going to go. All right. Now, our horizontal asymptote. So that's y equals. All right. What I say your horizontal asymptote always is. So if we look back on the previous page, what does it say the horizontal asymptote always is? Y equals k. Well, what's my k value here? What's my k value? 3. So that's equal to k. So that means our horizontal asymptote is at y equals 3. So in other words, whatever big number is being added or subtracted to the fraction, that's your horizontal asymptote. So that's right here. So these are our excluded values. So another thing you can think about your horizontal and vertical asymptote, they're your excluded values. So my domain for this function would be what? Your domain's always what? No. How have we been stating the domain for rational functions so far? Owen.
All real numbers except x does not equal 0.
Not x cannot equal 0. What can x not equal in this case? 4. So all real numbers except x cannot equal 4. What's the horizontal, or not the horizontal, what's the range? So range is y values. So how we've been stating the y values? Except y cannot equal what? 3. So guys, if you look, vertical asymptote, that's your excluded value in the domain. Horizontal asymptote, that's your excluded value in the range. They go hand in hand. So if you know them, you got your domain and range. Domain and range should be easy for these as long as you can get the horizontal and vertical asymptote. Now, we're going to then use Desmos to get the table. So in Desmos, remember you can go from -10 to 10. All right, I'm going to type in this problem. So I have 2 divided by x minus 4 plus 3. And I'm going to generate the table. I want nice, pretty whole numbers. So there are 4 numbers that you can get as nice and pretty. So I'm going to find them. All right, so remember, your axis guides you. So your axis goes from -10 to 10. So we're going to check all those numbers and see which ones we can get to be pretty. So we have 1 at 2, but let's check the rest. So -10, oof, not pretty. -9, not pretty. -8, definitely not pretty. -7, not pretty. -6, kind of pretty, but not pretty enough. -5, not pretty. -4, kind of pretty, not pretty enough. -3, not pretty. We know -2 through 2. 2 will work. So 2 is the first one that works. So that's the one we're going to use. So 2's first, and it will go to 2. So we got 2, 2. All right, let's keep going. So 3, oh, got another pretty one. Nice whole number. 3, 1. Keep going. 4. Well, 4 is undefined. Why? What's our domain? All x values except x cannot equal 4. So, of course, 4 is going to be undefined. All right, 1. Not pretty. Not 1. 5. Oh, 5 is pretty. So we got 5, 5. 6. Oh, 6 is pretty as well. 6, 4. And let's just finish it up. Just check the rest. So 7, not pretty. 8, kind of pretty, not pretty enough. 9, kind of pretty, not pretty enough. 10, not too pretty. So we got these points right here. Now, I don't mind if you use like a 0.5, okay? So if you see a 0.5, that's okay, but try to shoot for whole numbers so it lines up nicely. But if you can't find whole numbers except for like 1 or 2 of them, you can use 0.5s, okay? So if I graph this, I got 2, 2, 3, 1, 5, 5, 6, 4. So these points kind of tell me where I draw my graph. And the way you draw your graph is you kind of just go along with the asymptotes. That's why I say you draw the asymptotes first. So you go as close as you can to the asymptote without crossing it. And then you start to curve through those points. And then you go as close as you can to the other asymptote. So you go as close as you can to the other asymptote. So that's your first branch. Your second branch, same thing. You get as close as you can, turn at those points, and then get as close as you can to the other. And there's your graph. Addie, can you close that door, please? All right. So identify the vertical and horizontal asymptotes first because that'll give you an idea of where your graph is going to be. From there, you create a table using Desmos. And again, you want relatively pretty points, so either whole numbers or halves. So whole numbers or 0.5s. I don't care as long as it's within those two number families. All right. Any questions on that? Okay, let's try another one. So walk me through it. Let's get asymptotes. So we need our vertical asymptote and horizontal asymptote. So that'll be x equals and y equals. How do I get my vertical asymptote? Anyone? How do I get my vertical? We literally just did it. How do I get my vertical? Someone who has not talked yet today. How do I get my vertical? Right. Set the denominator equal to 0. Solve for x. So x plus 1 equal to 0. So Riley, what is my denominator? I mean my vertical asymptote. X equals what? Good. So x equals -1. So that's my vertical. So that'll be right here. Horizontal. Someone else. How do I get it? It's your k value. What's your k value? -4. So y equals -4. So that'll be right here. That's -6. Hope I actually put it on the right spot. So we got our two asymptotes. Let's go ahead and get our domain and range. What's my domain? Remember, it's based off your asymptote. So what's your domain? Someone who has not talked yet today. What's the domain? What have we been saying the domain is for rational functions? Except x cannot equal what? -1. Good. What's the range? Someone else. What's the range? Right, all real numbers except y cannot equal -4. All right, now we're going to get our table. So, going to plug the function in to Desmos. So I got -3 divided by x plus 1 minus 4. I'm going to generate my table. So gear key table. All right. Now, remember, I want to check however many I can fit on the axis. So I'm going to go from -10 to 10. Now, some of the ones that we got on the pre-generated works. So if we start at -10, not a pretty number. -9, not good enough. -8, definitely not. -7, it's okay, but not quite what we want. -6, okay, not quite the best. -5, it's okay. -4, oh, nice number. So we have -4, -3. Let's check -3. It's okay, but it's not the best. -2 is a nice number, though. It's -1. So -2, -1. -1 is undefined, which makes sense because that's where our vertical asymptote is. 0 is pretty nice because it's at -7. So 0, -7. And then 1's okay, but it's not the best. 2's pretty okay, though, because we got a nice whole number. So 2, -5. And I can guarantee you the rest of them will not be pretty. So we'll leave it to that. So I will say, guys, when it comes to these, there's typically 4 numbers that give you nice, pretty whole numbers with no decimals. There's usually about 4 numbers. So once you get those 4 numbers, you're done. Now, the only exception is if your numerator is 1. Then you got to use like the 0.5s. Okay? So if I graph this, I have -4, -3, so right here, -2, -1, 0, -7, 2, -5. So when I make my graph, I'm going to start as close as I can to my asymptote, turn at the points, and then get as close as I can to my other asymptote. So there's my first part of the graph. Second part, I'm going to start as close as I can to my asymptote, turn at the points, and then get as close as I can to the other. And there's my 2 graphs. So these graphs aren't really that bad to graph. You just got to be able to identify the vertical and horizontal asymptote. Which again, those aren't hard to do either. You can get it just by looking at the function. And guys, I can tell you right now, Math 3, you have a whole unit on rational functions. How do I know? I teach it. All right? You have a whole unit on rational functions, and they're harder than these. These are the basic ones. So the better you understand these, the better you'll be in Math 3. All right. Any questions on the graphing aspect? All right, so now I want to shift gears over to equations. All right, so go to page 38. So, first off, let's look at the first three. These aren't equations yet, but I do want to make sure that we can figure out which values make the fraction undefined. So for A, how do I figure out which values of x make the fraction undefined? We do what? Set the denominator equal to 0 and solve for x. So if I add 2 to both sides, x equals what? 2. So the value that makes the fraction undefined, x equals 2. Or you can put x cannot equal 2 either way. I don't care. What about for b? That one's pretty easy. What's b? If I set this denominator equal to 0, what's my excluded value? 0. X equals 0. C. So if we set this equal to 0, let's solve. So I add 1 to both sides. I have x squared is equal to 1. Then what do I have to do? Square root both sides. So x is equal to square root of 1 is 1, but what do I have to put in front of it?
Square root.
Nope. Nope. It's a what? I heard it. It's a very special symbol. Plus, minus. Good. So you have to put a plus minus in front of it. Remember, whenever you're solving and you take a square root, you got to put the plus minus in front of it. Meaning, our values that can't work are both -1 and +1. Which that's true because if you plug -1 back in for x squared, that's 1 minus 1. 1 squared is 1, minus 1's both give you 0. So like I said, you can have more than one excluded value. All right, so you got to be careful, especially if you see an x squared in the denominator. That typically means you'll have 2. Now, we are going to solve rational equations, and we're doing the very, very basic ones, which are proportion-like. So we get to do everyone's favorite thing, cross multiply. Solve the resulting equation, which will typically be a nice linear or quadratic. And then we got to check for extraneous solutions. So remember, we talked about extraneous with radical. What does extraneous mean? So we did this with radical equations. I always told you to check for extraneous solutions. What does extraneous mean? It's a solution that does not what? It's a solution that when we plug it back in for x, it doesn't do what? Starts with a W. 4-letter word, starts with a W, ends with a K. Work. It doesn't work. So it's a solution that doesn't work. In this case, it's whatever makes the fractions undefined. Or if we plug it back in, the denominator is equal to 0 when we plug it back in. All right. So in reality, you really only need to plug the x values back into the denominator. Just do a quick check. So let's try some of these. So this first one, we start by cross multiplying. So I have 5 times x minus 2 is equal to 3 times x plus 4. So now we got a nice little linear equation. What's my first step to solve? So we cross multiplied, so how do I solve this equation? Come on, guys. You start by doing what? Distributing. Distribute on both sides. So this would be 5x minus 10 is equal to 3x plus 12. What do I do next? How? So I need to combine like terms, but right now they're not on the same side of the equal sign. So how can I? So I can minus 3x to both sides, and I can do what? So this will give me 2x minus 10 is equal to 12. Then what do I do? Add 10 to 12. So 2x is equal to 22. What's the last step? Divide by 2.
both sides by 2.
So x is equal to what?
11.
Now, before you say that that's your answer, just do a quick check and plug it back in for x in the denominators, just in the denominators. Because remember, you don't want the denominators to equal 0. So 11 plus 4, that's definitely not going to be 0. 11 minus 2, that's definitely not going to be 0. So this works. So just in the back of your mind, just check the denominators really quickly. Okay, let's try another one. So what do I do first? What do I do first? Cross multiply. So I have x minus 3 times x minus 4 is equal to 2 times 1. Now, on the left side, what do I have to do to multiply that through?
You have the FOIL.
FOIL or box method, right. So if I do a quick box, x minus 3, x minus 4, x squared minus 3x minus 4x, 12. So this would be x squared minus 7x plus 12 is equal to 2 times 1, which is 2. Now, what type of equation is this? Is it linear or quadratic? I know you guys noticed we had like 2 units on this. What type of equation is that? It's quadratic. So to solve it, I got to get one side equal to what first?
0.
0. So I'm going to subtract 2 to both sides. I got x squared minus 7x plus 10 is equal to 0. Now, this is factorable. So I'm going to do big X. What goes on top? 10x squared. What goes on bottom? Negative 7x. So what are 2 factors of 10 that'll add to negative 7? Negative 5 and negative 2, because we're adding to negative 7. Do a quick reverse box. I have x squared, negative 5x, negative 2x, and 10. GCF of the first row? X. GCF of the second? Not just 2. Negative 2. First one's negative, so you got to take out the negative. GCF of the first column? X. GCF of the second column? Negative 5. So your factors are x minus 5, x minus 2 equal to 0. So then finally we set both equal to 0 to solve. So x is equal to 5, x is equal to 2. Plug both back into anywhere I see an x in the denominator. So that's just in this denominator. We got to make sure it's not 0. 5 minus 4, that's 1, not 0. 2 minus 4, that's negative 2, not 0. So these both work. So x is equal to the set of 2 and 5. So just know quadratics come back to haunt you. You've seen them in radical equations. You'll see them in rational. All right. Let's try another one. So example 3. I don't want to do that one. Let's do example 4. So what's my first step? Cross multiply. So I have 1 times x squared plus x minus 2 is equal to 2 times x squared minus 1. Distribute. Since I'm multiplying by 1, that all stays the same. Then I get 2x squared minus 2. So it's definitely a quadratic again, so I have to get one side equal to what?
0.
0. Which side am I moving? Remember, you always want your x squared to be positive, so which side should I move? The left or the right?
Right.
No. Definitely the left, because the right has the bigger x squared. So I'm going to subtract x squared, x, and add 2 to both sides. So subtract x squared, subtract x, add 2. I get 0 is equal to x squared minus x, and the 2's cancel out. Well, that's an easy factor. We don't even have to do big X. What's the only thing that I can factor out of x squared minus x? Guys, what's the GCF? X. I can only factor out GCF of x. So x times x minus 1 is equal to 0. Set them both equal to 0. X is equal to 0. X minus 1 equal to 0. So we get x is equal to 0. And if you add 1 to both sides, x is equal to 1. Now do a quick check plug back in. So 0. 0 squared, that's 0 minus 1. That works. Just doesn't give us 0. 0 squared plus 0 minus 2. That gives us negative 2. That works. Now 1. What's 1 squared? Minus 1. What's 1 minus 1?
0.
So does 1 work?
Nope.
Nope. Because 1 squared minus 1, that gives us 0. So 1 does not work. So it is what? Extraneous, meaning what do we do with extraneous solutions? What I tell you to do with extraneous solutions? If they don't work, should we include it in the solution?
No.
No, you throw that sucker out. So your only answer that works is x equals 0. That's why I say you gotta check extraneous. It will happen. All right. Okay. I want you guys to try example 5 on your own. Let's give it a shot. So start by cross multiplying. Do any box methods or distributing that you need to. And then solve based off of the type of function. So if you still have an x squared and it's quadratic, at one side equal to 0. If you don't have an x squared, it's linear. So just solve for x like normal. And make sure you check for extraneous solutions at the end. I'm gonna give you guys one more minute. All right, check your answer. Now, I didn't do all the steps for factoring, but that's what I got when I finished factoring here. And if you plug both the answers back in, 3 plus 3 is 6, 1 plus 3 is 4. No denominators are 0. So they both work. Any questions on that one? How'd you guys do?
Miss Murphy, did you just, I'm just, copying this down.
Yeah.
Thanks. All right, thanks.
You guys good? All right, one last thing I want to talk about. We're not going to solve example 6, but I want you guys to recognize something. So, if both sides are not fractions, you can make it a fraction because I can put the 3 minus z over what? 1. So if you don't see fractions on both sides, make the one that's not a fraction by putting it over 1, and then you cross multiply. Okay? That's the only thing I wanted to bring up. Any questions on solving proportionals? Okay. So you got like 10 minutes left of class, so you can work on your delta mass a little bit if you want to. I also need you guys to erase your whiteboards, and if you could take the graphs off of them and put them back under the shelf, that'd be great. Make sure they're erased though. So make sure the graph parts are erased as well, and take them off and put them back under the shelf. Oh, yeah. Huh? So 4x times 3 is 12x. Negative 1 times x is negative 1x. 12x minus 1x is Guys, everybody's putting 3 calculators in the same spot. That ticks me off. We'll separate them.
You watch football? You watch football? You like? Yeah, the draft starts from. If you have second period plan, where's my shirt? Just keep peeling down. That's fine. Or something. Y'all just lost next year.
So guys, if you ever wonder what math 3 looks like, here you go.
Yeah, I skip that.
Nope. Yeah,
Yeah. I feel so bad for high school days. Ratio 5 days. Maturity. Joe.
Yeah. Really protected. They have the third overall pick.
I wish I could have done
I'll take
Want to go for one down? Can I say
one down rest right now. Those are probably yeah. They're predicting we're going to get 3 ARs.
I don't want to slip things because I'm going to cheat off my paper and the teacher thought I was
Hey,
so they
hands
go
off my chest.
Yo, stop this in chat. Oh yeah.
I know, so you punch that pocket back in. Bro,
Are you gonna get the ion? You get the ion.
I'm gonna get the only eye. Just like that.
Dude, that would be so peak.
I
I think all of us should switch to the red ion. Everyone. Make it mandatory. How much is it? Like $160. Put it on sticker. On pulse too.
For not strong, it's 120. Strong, it's like 180.
Dude, just get somebody cheap.
Get Scott brand.
Scotch.
This was last student work. She didn't hit me on the head of my paper. It's like, I don't care if you know my mom. Why are you hitting me with paper?
She knows she has it.
You would like that. You be brothers? Yeah. You trying to run a
That's great.
Have you seen Elijah, bro? He's like skinny and has like ginger facial hair now. Oh my god, oh my god. I'm so glad you get on TikTok. Avery. Yes. She's a what? Wait. What?
chef. Going to the state where Scott's going?
No.
Yeah, it seems like
You.
yes.
No. 4 from that.
Or I'll be Taylor Avery University.
Where did Riley go? She like
Okay, buddy, I'm just gonna let you be delusional now.
I actually
she's gone. She dropped herself.
Go to ECU, bro. Go to Frog.
I'm not going to the yet.
I go there all the time. Excuse me. Sorry. They're like that's.
Yeah.